Let's dive right into this explainer. Today we're tracking the incredible evolution of language model prompting. We're talking about the journey from typing basic, single-command prompts all the way to engineering fully autonomous digital workers. If you've been wondering how AI is making that massive leap from just answering simple questions to actually executing really complex multi-step goals, well, you're absolutely in the right place.
We've got a packed roadmap today. 1. Basics, 0, and few shot. 2. Chain of thought. 3. Self-consistency in prompting. 4. Tree of thoughts. 5. The React framework. And finally 6. From prompts to agents.
Section 1. Basics, 0 and few shot, the foundation of prompting.
To really grasp how far we've come, we have to start at the beginning. You see, this whole evolution actually mimics human cognition. Standard language models operate a lot like our own System 1 thinking, right? They're fast, they're automatic, and they basically just generate tokens sequentially, left to right. But to solve truly complex problems, we have to push AI towards System 2 thinking, which is much slower, highly deliberate, conscious, and crucially, capable of autonomous planning.
The absolute most basic way we interact with an LLM is zero-shot prompting. This is the ultimate System 1 test. You literally just hand the model a high-level objective with 0 prior examples and rely completely on its pre-trained knowledge to figure it out on the fly. Think about asking an AI to, say, write a poem about a cat without any other instructions. It's great for simple stuff, but as you've probably experienced, it fails pretty reliably when you give it complex tasks that need a structured sequence of actions.
So when zero-shot fails, we step up to few-shot prompting. Here, we're anchoring the model. We do this by throwing a few concrete input-output examples right into the prompt itself. So for instance, you might show the model 3 examples of exactly how you want a date formatted before asking it to format a 4th. By showing it what a successful execution actually looks like, we give the model a clear pattern to follow. And that significantly boosts its reliability on structured tasks.
Section 2. Chain of thought. Reasoning step by step.
But what happens when the mapping from the input to the output isn't so trivial? What if the model needs to solve a complex math problem or apply some common sense? That brings us to chain of thought, or COT. What's really fascinating here is how COT forces the model to hit pause and actually reason. Instead of just blurting out a final answer and hoping for the best, COT prompts the model to generate intermediate steps, like writing out the intermediate equations of a math problem before spitting out the final number.
However, even with the step-by-step logic of COT, it still struggles with tasks that require strategic look-ahead. Researchers actually tested this on the game of 24. That's a mathematical reasoning challenge where you have to use 4 numbers and basic arithmetic to get exactly 24. And guess what? With standard chain of thought prompting, the state-of-the-art model achieved a mere 4% success rate. Just 4%. It turns out, sequential left-to-right decoding just isn't going to cut it when you need to plan ahead.
Section 3. Self-consistency in prompting, the ensemble approach.
To improve upon standard chain of thought, researchers realized something important. Complex problems usually have multiple valid reasoning paths, right? If one path fails, another one might succeed. This led to self-consistency. It's an ensemble approach. Instead of generating just a single chain of thought, you prompt the model to generate multiple independent reasoning paths for the exact same problem. Then, you look at all the final answers and just take the most frequent one. By letting the model essentially vote on the final answer, success rates on that Game of 24 challenge bumped up to 9%. Better, sure, but still nowhere near enough for true autonomous problem solving.
The crucial takeaway here is that both of these techniques still have severe limitations. They don't locally explore different continuations within a thought process, and there is absolutely no mechanism to backtrack. So, if the model hallucinates a fact or makes a silly math error early in the chain, that error just cascades, and the entire output is ruined. It goes completely off the rails.
Section 4. Tree of thoughts, deliberate problem solving.
This technique represents a massive leap in that deliberate System 2 thinking we talked about. It completely changes how we conceptualize the AI's problem space. Tree of thoughts, or TOT, allows the language model to maintain an actual tree of intermediate thoughts. So instead of a single linear chain, TOT creates branches. It proposes multiple next steps, actively self-evaluates whether those steps are actually promising, and can even look ahead or backtrack, exactly like a human being trying to solve a tough puzzle.
In action, you can picture this as a literal tree structure. Back to our Game of 24, the model proposes a few different intermediate equations. Then, it uses a value prompt to deliberately evaluate the state of each branch, marking them as sure, likely, or impossible. If a path is deemed impossible, no problem. The model just prunes that branch, backtracks, and tries a completely different route.
And the data on this is just staggering. By giving the model the ability to explore and discard bad ideas, Tree of Thoughts skyrockets the success rate on the Game of 24 to an astonishing 74%. I mean, it literally turns a task that the model almost universally failed at into one it can reliably solve over and over again.
Section 5. The REACT Framework, Synergizing Reasoning and Acting. Now, while Tree of Thoughts is incredible for logical puzzles and creative writing, what about tasks that require real-world knowledge? Knowledge that the model might not have actually memorized during training. As we touched on earlier, if a model doesn't have access to the external world to update its knowledge, a single hallucinated fact will derail the entire reasoning process. Because let's face it, you can't just think your way out of not knowing a specific piece of external data.
Enter REACT, which stands for Reason plus Act. REACT interleaves reasoning traces with task-specific actions. This is a game changer. It means the model isn't just sitting there thinking in a void. It's actively interacting with external environments, like hitting a Wikipedia search API or querying a database to retrieve reliable factual information to ground its next thought.
And this builds into a really elegant, continuous loop. It goes exactly like this. Thought. The model reasons about what it needs to do next. Action. It invokes a specific tool, like a search engine. Observation. It reads what the tool returned. And it just repeats this cycle until the goal is completely met. The reasoning helps target exactly what to retrieve next, and the retrieved information perfectly grounds the reasoning.
Section 6. From Prompts to Agents, the Shift to Autonomy.
By mastering these techniques, from basic few-shot all the way up through Tree of Thoughts and REACT loops, we cross a massive threshold in software engineering. We move from standard generative tools to true AI agents. There's a great quote from the Agentic AI roadmap that perfectly summarizes why this matters so much. The leap from generative AI to agentic AI is the shift from a chatbot that waits for instructions to an autonomous worker that executes goals. We're moving away from having brilliant interns who just answer questions to autonomous digital workers capable of executing high-level objectives totally on their own. When you combine REACT loops and TOT reasoning, you start building the three core pillars of agentic AI. First, planning and task decomposition, using techniques like plan and solve, so the agent doesn't just react blindly to everything. Second, a memory ecosystem. This includes short-term working memory and long-term vector databases. And third, the action layer. Now this one is absolutely crucial. Tools must be built to fail gracefully. If a database query fails, the tool shouldn't crash your whole program. It should pass that error right back to the LLM so the agent can actually reason about what went wrong and try a different approach.
I really hope this explainer has demystified these advanced prompt engineering techniques for you. The builders who master this orchestration layer, they are the ones architecting the next generation of software. So I leave you with this final thought to ponder as you start building your own autonomous systems. As we shift from applications that just compute to applications that reason and act, what autonomous system will you architect next? Thanks for joining me on this explainer.